You can see that I'm not a professor of computer science. I always need help. So I was planned to speak a little bit about deep learning, about machine learning. That's so the course I started yesterday here in a lecture in the MIT classroom is linear algebra and also machine learning. So, oh, good. And these are the slides for linear algebra, and then you'll see some machine learning in action. Okay, so that's me, and I'm at MIT today. Finally, thank you. And okay, Andre, we could go on to the next slide. Shows maybe the two books or three books, actually. The most known maybe is the first one, Linear Algebra, Introduction to Linear Algebra. It's now the 5th edition, and that's the textbook for the Math 18.06 at MIT and the videos. And then the next middle book there is the newer book that includes learning from data. So that will be part of today's presentation. And then I just, you see on a third book is a shorter linear algebra book that I wrote during COVID. So I had a good time. I was, of course, only at home every day. So I thought, what can I do? I'll write a more interesting, a new linear algebra book. So the video lectures, maybe you know the URL is OCW for opencourseware.mit.edu/courses, and then you go to the course that you choose, engineering, math, everything. MIT has like 2,000 courses available. Okay, and then for the books themselves, you could email me about the book, yeah, if you wanted a copy. So there's only hard copy, no. I'm sorry, there's not a ebook. Okay, ready for mathematics now. Okay, so let's see. So starting with the learning function, just for a few lectures. Now, maybe you know how learning functions work. They involve matrices, so a lot of linear algebra, but they must use something nonlinear. And that's this simple nonlinear function, piecewise linear. It's 0 for negative y, and it's equal to y for positive y. And for some reason, it's called ReLU, is the nonlinear thing that's used at every level, for every neuron in the neural net. So let's see a picture of the neural net, or part of the neural net in the next slide. Yeah, the next slide has, yeah. So here is only one hidden layer. So the inputs are on the left, V1 to VP. Those are the, if you, suppose we're trying to recognize a handwritten number. Suppose a number is written 0, 1, 2, 3, 4, up to 9, one of those numbers, and we're trying to find which number it is. So the V's are the from the pixels of the image. So we have an image of a number like 3, and we divide that image into pixels, and their strengths are V1 to VP. Now comes the matrix. So a matrix A multiplies V. Maybe it's a 4×3 matrix, let's say, or 3×4. Yeah, and we get AV, A times V. And now comes this ReLU, this nonlinear step. And actually we add a vector B as well as multiply by A. But anyway, that's the step. And now with only one hidden layer, we go to the output. So that's a very short neural net, and many of you will know much more about that. Okay, so let's Let's now take go to the next slide and see what, oh, this is good. This is really what I want you to see. It's a Google, a person who works at Google near MIT created this interesting way to have some experiments, real experiments with a neural net. And over on the left you see a little box around one picture. So that's the input. The input is blue dots that are +1 and orange dots that are -1. And we're looking for a function, a function of x and y, which will give us plus on the blue dots and minus on the orange dots. Okay, and that function is created by those matrices. So Andre has pressed start, and so already it's done 300 iterations. Soon will be 1,000 iterations, but it has already done the job. You see in the big picture on the right, you see it's really the graph of the function. It's showing where the function is positive, where the function is negative, and in between where the function is 0. So it's exactly right. It separated the blues from the orange. It's plus for blues, minus for oranges, just what we want for our function. So now we've trained it, and now we would use that same function for new data that the system has not seen. So, but let me just repeat the URL, because you can do all this yourself. playground.tensorflow.org. Okay, now let's do one more example. So let's go to the next example, which is much more difficult. Okay, now look over at the far left. You see it's a lot of spirals now. It's orange spirals are going inside blue spirals. So it's very hard to create a function. There you see it. We now want a function created by our neural net. So it's only going to be a linear function, piecewise linear, which has the opposite sign on the blue and the orange. So now we're only using 2 hidden layers, not enough. So if Andre could add another 2 hidden layers, you see, Andre will just click on the picture there up at where it says hidden layers. Yeah, right there. Let's do plus, do some more layers, and then maybe put more neurons, more points. So just below that, where you do another plus, good, and another plus maybe, and another one on the next one, just to give some. Now it's a bigger, of course, everybody knows the real systems have thousands and often millions of neurons. Here we have 4, 8, 11, maybe 13 neurons. Well, now let's push start on this one. Okay, start. So now it's trying, has a little graph of the error. You see it's trying in the picture on the right. It's taking steps. It's doing a minimum. This is a big minimization problem. Minimize the error. Minimize the difference, what we want from what we have. Yeah, so it will struggle. And now it's already done 1,000 iterations, and it's trying its best. I always feel sad about it, because we have, it might, if we keep going, it might get, do you see that no, it hasn't done very well. So this is for you to go yourself to playground.tensorflow.org, give it more layers, give it more neurons on each layer, and watch, and then you have the good feeling of seeing the function that you want, separating the blue dots from the orange dots. I hope that's interesting. So now we're up over 2,000, but It's, oh, well, yeah, that looks pretty good. Oh, that's almost success, isn't it? At 10,000, 10,000 iterations. It's almost successful. Yeah, I see a few blue dots still in the orange part. Okay, back to mathematics. That was the fun. Okay, and back to linear algebra. So I have a matrix. I want to understand that matrix A. It has m rows, it has n columns. It could be big, it could be small. There are small matrices here on the slide. And I want to understand that matrix. So a good way to understand it is to understand its column space and its row space. So the column space is all combinations of the columns. Those columns are vectors. You can take combinations. So you can take 2 times column 1 minus 5 times column 2 plus 11 times column 3. And so you get a whole lot of vectors. They fill a plane in some, maybe a high dimensional plane, but it's linear algebra, so the plane is flat. And yeah, so I'll just read the line. The column space contains all combinations of the columns. And the column space is a whole lot of vectors, a whole lot of column vectors. All this, it's a flat plane or a three-dimensional surface or just a line. Let's see, look at the end of this slide, you see some examples. So the column spaces of the identity matrix, well, that's all combinations of 1, 0 and 0, 1. So we will get any vector xy, we'll get the whole xy plane. And 1, 2, 3, 4, that will also give us the whole xy plane because 3, 4 is in a different direction from 1, 2. So they're independent. Now, the next line has a 1, 1, 2, 2 matrix. Well, that matrix, the column, the 2, 2 column is dependent on the 1, 1 column. It's in the same direction. It's just 2 times as long, but the direction's the same. So when we take combinations of 1, 1, 2, 2, we just stay on that line. So the column space of those matrices are lines, one-dimensional subspaces. Oh, and then finally at the bottom, I put the 0 matrix. And of course, the only combination of those columns is the 0 vector. So that's 1 point. Okay, so those are column spaces of very small matrices. Okay, but we need to understand column space. Okay, on to the next slide. Yeah. So the row space is similar, but it has all combinations of the rows. And if I want to stay with column vectors, then I just would transpose the matrix, change A to A transpose, AT, make the rows into columns, and then I would do the column space of AT, A transpose. Yeah, so those are examples. Again, oh, now we're up to 3 by 3. And you see the first 3 by 3. Yeah, do you see that only 2 columns are independent in that middle one? Because 1, 1, 1 plus 2, 3, 4, it equals 3, 4, 5. So 3, 4, 5 we already have, it's not new. So we only have 2 independent columns. And actually we only have 2 independent rows. That's the wonderful first great fact in linear algebra, that the number of independent columns, which is 2 for this middle matrix there, equals the number of independent rows. Now I don't really see that. I've got 3 rows there. I'm looking at the rows 1, 2, 3, 1, 3, 4, and 1, 4, 5. And I'm pretty sure those columns, those rows are dependent. I think that 3rd row is some combination, which I don't know, of the first 2 rows. If you might want to figure out what combination it is. Why do I think it is a combination? Because I know the the theorem that the number of independent columns, which is definitely 2 there, that definitely has 2 independent columns, then it will have 2 independent rows. And so somehow only not 3. Okay, so you see the examples. Below that, the other 3 by 3 matrix, well, it's easy because it's triangular, and we can see that no column is a combination of other columns. Those 3 columns are independent. So a triangular matrix is good as long as you don't have any zeros on the main diagonal. So this is just fun with matrices, but I'm aiming to understand with these small examples the ideas. So what ideas do we have so far? Independent columns and dependent columns, independent rows, dependent rows. And now the word rank is the number of for one matrix, the rank was 2. For the other matrix, the rank is 3. Okay, let's go on to the next slide and see more examples. Well, this is, we've understood this. This is dependence. Yeah, this is dependence. All those examples have dependent columns. The first, you see why. A1, column 2 is just 2 times column 1. And A2, oh, it has a 0 column, a column of 0. So that is the 3 columns don't go into 3 separate directions because 0, 0, 0 doesn't get started. And finally, A3, there will only be 2 independent columns in 2-dimensional space. Okay, you're ready for the next slide. These are examples that you know. Okay, and now, yeah, so this is saying what I've just already said. A key idea, there's a box around the key idea. Number of independent rows equal number of independent columns. That number is the rank. Yeah, and for that triangular matrix U at the bottom, the 3 columns are independent and the 3 rows are independent. So the rank is 3, full rank for that matrix U. So it has an inverse matrix. Okay, ready for the next slide. We're moving along. Okay, so here's how I find the independent columns. I start with column 1. I put it into the C matrix. C is the matrix of independent columns in C. And if column 2 is not a multiple of column 1, that column 2 goes into C. If column 3 is not a combination of columns 1 and 2, 3 goes into C, otherwise not. So you just go from left to right, and you end up with the matrix C, the column matrix, the independent column matrix, right? So here, now just let me say again. We're given the matrix A. It has some independent columns, but then it may have some dependent columns. So we construct C with, C is our column matrix with only the independent ones. So every column in A is some combination of the columns in C. C has all the good ones, all the independent ones. And the matrix R tells us what that combination is, because you know how to, well, I'm multiplying matrices now, C times R. So what that does is it takes combinations of the columns of C, and the columns of R tell me which combinations to choose. Okay, C times R. Matrix multiplication is more interesting than you think. Okay, let's go to the next slide. Yeah. Okay. So, there's a case of A equals CR. So this is what we need to know. You see the matrix with columns 1, 1, 2, 3, and 4, 5. Those 3 columns are dependent. The first two columns go into C, that's 1, 1, and 2, 3, 1, 1, and 2, 3. Those are independent. And now R tells me, the last matrix is R. R tells me how to get every A column from the C columns. So you see the first column of R, the first column of R has a 1 and 0, so that's, I take 1 of the first column to get the 1, 1 vector. The second column of R has a 0 and 1, so I take 1 of the second column, 2, 3, to get the 2, 3 matrix of vector in R, in A. And then finally, the interesting one, the combination, I take 2 of the 1, 1 column plus 1 of the 2, 3 column. That gives me 4, 5, the dependent column of A. Do you see how A equals CR? It has to be, when we create it, it must work, because we put the independent ones in C, and then R tells us how to get all the columns from the independent ones. And because matrix multiplication, the number of columns in C equals the number of rows in R, 2 columns, 2 rows, 2 columns in C, 2 rows in R, then those are, C tells me all about the column space. R, the rows of R tell me about the row space. And I had 2 columns in C and I had 2 rows in R. So those spaces have the same rank, same dimension. So this is my lecture, full speed for my linear algebra class, and it would also be somewhere on the 1806 website. And actually, I'm teaching the class, my second, we just started the spring semester. Well, it's one foot of snow is outside here, so it's not spring, but we call it the spring semester. So I'm my second class in this semester, so I don't know the students yet, about 60 students. I'll be explaining A equals CR in that class. Yeah, okay, so that's a wonderful thing. Now, then comes the big picture of linear algebra. In the next slide, maybe, might be, hope so. No, this is another review. We don't need a review. We understood the thing. Okay, so let's go on to the next slide. Yes, here's the big picture. Here's the big picture. So for any matrix. So yeah, let me take time on this one, because this is probably, this is on the cover even of the Introduction to Linear Algebra book, the Four Subspaces. And so we have a matrix. From the matrix, we find the column space. You see the column space over on the right there. And we have the row space. So the column space, again, is all combinations of the columns. And when we take all combinations, we get the whole space. And on the left, the row space is all combinations of the rows. And again, those spaces are the same dimension. That's what we just understood. That first great fact in linear algebra is, and if you had a matrix which was 1,000 by 2,000, well, to know that the number of independent rows equals the number of independent columns, that's not simple, but it's true. It's always true. So those two spaces, they account for the independent columns and rows. But now the other two spaces are the solutions to AX equals 0 for the null space, null meaning 0. So they're the solutions to, they have the vectors in that give combinations of the columns that produce the zero vector, the zero column. So that's the null space. You can see that it's sort of the opposite of the row space. From AX equals 0, the equation for a vector in the null space. So that vector X is in the null space. If you multiply A by X, if you multiply a matrix by a vector, then the usual way to do it is dot products of the rows with the vector X, right? When you multiply AX, you take dot products, inner products of the rows of A with the vector X. And here, the vector X is perpendicular to the rows, 90-degree angle, so we get 0. Yeah. So it's natural then that the null space, the X's, are perpendicular to the rows in the row space. Do you see the beauty of this picture? We have the 4, if we know those 4 spaces, then we know about the matrix, those 4 subspaces. We would need to know the rank, and we would need to know which vectors are independent to know which vectors are in which spaces. Yeah, that's a good picture to understand. And then then a big step is to choose basis vectors in those spaces. So do you remember the meaning of a basis? So let's look at the column space. So what is a basis for the column space? It's the independent columns. It's the R independent columns is a basis for the column space. And R independent rows are a basis for the row space. And the matrix A is behind everything. The matrix A is behind everything. This is the big picture of a matrix. Okay. By the way, here's my first homework problem. Suppose the matrix has, suppose there's only one independent column. Every column is a multiple of column 1. Okay, that's a very special, simple matrix, a matrix of rank 1. So every column is, so what's a matrix of rank 1? The columns might be 1, 3, and 2, 6, and 4, 12, and -5, -15, all in the same direction. Then the rows are in the same direction. That's a challenge. To prove the great fact of dimension equal dimension for column space and row space, when that dimension is just 1. So let me ask you the question. This is the homework question for fun, of course. For every linear algebra is fun. So that's the question is, prove if all the columns are multiples of column 1, then all the rows are multiples of 1 row. So an example would be to have the columns 1, 2, and 3, 6. So the columns are all in both columns in the direction of 1, 2, and 3, 6. And then the rows are in the same direction, 1, 3, and 2, 6. So for 2 by 2, my challenge is easy, but now prove it for any size matrix. Yeah, okay, good. So we're moving along. My lecture might not take all 50 minutes, but that's okay, I'm sure. So shall we go to the next slide? Not forgetting that big picture. Oh, and then that rank, the M and N and R, those are the key numbers. How many solutions to AX equals 0? In other words, how big is the null space? Well, the row space had dimension R, so the null space has dimension N minus R. That tells us how many independent X's, how many independent solutions to AX equals 0. And of course, if our matrix has many columns, so N is a large number, many columns, then there will be solutions, because the rank can't be greater than M. So if N is larger, then we have some solutions. Some N minus R would be a positive number, and we would have some solutions in the null space. Yeah. Okay. Now, so this is basic linear algebra about a matrix A. But now I want to jump to the end of the linear algebra course, which is about singular vectors and singular values. Everybody has, if you've studied linear algebra, you know about eigenvectors and eigenvalues. So eigenvectors and eigenvalues come from a square matrix. But in data science, matrices are not square. We have two different, we have all the samples and all the observations. Two different rows and columns are different. And the number of rows is not the same as the number of columns in an experiment. So eigenvalues are not possible. If the matrix is rectangular, eigenvalues are for square matrices. So what do we do if the matrix is rectangular? It hasn't got eigenvalues and eigenvectors. And if you know the important idea of singular values and singular vectors, so those take the place of eigenvalues and eigenvectors. Yeah. And the singular vectors, they also fit the big picture, our four subspaces. The singular vectors are a good property of singular vectors is they're perpendicular to each other. We have a perpendicular basis, an orthogonal basis. The rows may not be orthogonal, but combinations will be the singular vectors. So this is the wonderful thing, that there's the four spaces have basis vectors that are perpendicular to each other. And the matrix A, acting on a vector in the row space, a singular vector in the row space, gives a singular vector in the column space. Yeah, let me try to give an example. So this is the singular value decomposition, and it's it tells you it tells you so much about the matrix. So let's look at the next slide. Maybe we see. Yes, good. This is a good slide to look at. Okay. So look at the equations at the top. You see the matrix A. So the matrix A is not symmetric. It's small, so I made it 2 by 2 to be so that I could show you an example. So it's the 3, 0, 4, 5 matrix. It's not symmetric. Well, so it would have eigenvalues 3 and 5 because it happens to be square, but I'm looking for singular vectors and singular values. That's different. Okay, so just to show, so if I multiply that 3045 by 1, 1, I get 3, 9. Okay. And then on the after that equation, I had another equation. I multiply 3045 times minus 1, 1, and I get, you see that multiplication, it gives minus 3, 1. Now, what is special about those two possibilities, A, V1? So what's special about V1? V1 was the 1, 1 vector, and V2 is the minus 1, 1 vector. And what's interesting about the vectors 1, 1 and minus 1, 1? They're perpendicular. They're orthogonal. So those two vectors, those were input vectors. They go in. And so I have orthogonal input vectors. Now, what vectors came out? Well, 3, 9 came out from the first one, and minus 3, 1 came out from the second one. And what's interesting about those vectors, 3, 9 and minus 3, 1, they're perpendicular. So I have this wonderful situation that the inputs V1 and V2 are orthogonal, and the outputs U1 and U2 are orthogonal. And that's what you want for the SVD, for singular values and singular vectors. So those are the singular vectors. Those are this is a big application is PCA, principal component analysis. And these are the principal components. These are the vectors you want. These are the vectors that take the place of eigenvectors. But now we have two families. We have V's and we have U's, because the matrix has M and N. It has an input space and an output space. So the great theorem is that every matrix has, for every matrix, there you can find U's and V's. The V's are orthogonal to each other. The U's are orthogonal to each other. And the AV is equal to the constant sigma, let's say sigma, the singular value, times U. AV equals sigma U. That's the equation we're looking for. AV equals sigma U. That's the equation that takes the place of AX equal lambda X. So can I just say that again, and then we're nearly at the end. So AX equal lambda X, that's the eigenvalue equation. Vector X goes in, a vector lambda X comes out. That's for a square matrix. Here we have vectors V going in, multiplied by A, vectors U come out, and the V's are perpendicular and the outputs are perpendicular. So maybe the next slide has a picture of this thing. Oh, no, this has more algebra. Yeah, this is a big part is played by A transpose A and AA transpose. Yeah, so there's more to say about the singular value decomposition, but let's go to the next slide with its picture. Yeah. So this is saying that every matrix, for every matrix, rectangular, there's a matrix V, a square matrix with orthogonal columns. That's called it's called an orthogonal matrix. And there's so every linear transformation, every matrix is is a rotation followed by a stretch, followed by a rotation. That's, and of course, this audience may know all about the SVD, but that's the great result from a linear algebra course for data science, because these vectors are the principal components that give you the information you want, that the information hiding in the matrix is revealed by U and sigma and V. Yeah, so this is a great part of linear algebra. Good. Okay, let's just look at the last slides and then I'll, yeah. Oh, and the very special thing about these vectors is that if you just want an approximation, you just keep the biggest singular values. If you want the best approximation to the matrix A, you just keep a few of the singular values and the singular vectors and not the rest. Yeah, so that's a great fact. Okay. So now let's just look at the last slide. It's probably sort of, oh yeah, this is a picture of the SVD for a 2x2 matrix. It's if you have data that's close to a line, that line is in the direction of the first singular vector of the first special component, right? So that's so here with linear algebra, we started with column space and row space. And then we found the perfect basis for it coming from the SVD, the singular columns, the singular vectors in the row space, singular vectors in the column space are the perfect vectors to be the basis for those spaces. Okay, that's a review of linear algebra. That's what maybe a first course in linear algebra would start with column spaces and end with SVD maybe. So thank you very much for inviting me to be here today. Thanks.
Thank you very much for your informative and exceptionally good speech, Professor.